Hi, and welcome to today's session on conformal predictions. Conformal predictions are a way to, instead of just giving a single prediction or like a single predicted value or score, to actually provide prediction sets or prediction intervals depending on whether you're in a classification or regression example. So specifically, they provide reliable uncertainty sets for any black box machine learning models. So the key idea is that you can have coverage that you can actually audit. So the true value will be covered about 90% of the time, for example, if you choose your value or your level to be 90%. It gives you prediction sets or intervals and not just the scores. So instead of, for example, here, if we look at this point prediction of 72%, you will actually then get this interval here of, for example, from 62 to 83. And the intuition behind that is that you use a held out calibration set to ask how large must our intervals or sets be so that past errors would have been covered. So how it works specifically is that first you split your data. So you need this calibration data set that is separate from your training data set. And then you just, as the next step, just train your model like you would normally do. So you can use any kind of model. So it doesn't matter whether you use a complex neural network, a random forest, XGBoost, any kind of regression or classification model. It really is model agnostic. You can use that for all the different models. Next, you calibrate your errors. So you basically compute then this non-conformity scores on this held out data set which you split in the very first step. Which basically, this is the important part because it gives you for your data set the the usual spread of errors, like what can we expect. And this you will then use on your predicted sets. So then you choose your interval or your label set using this empirical quantile from the step number 3. And the nice thing is that this gives you a marginal coverage guarantee. So the probability that your true label Y, so we're basically here, the probability that your true label Y is in the calibration set given your data is guaranteed to be larger than 1 minus alpha, where alpha is the level that you choose. For example, if it's 10%, you get your 90% coverage guarantee. So taken all together, this gives you the probability that the true label Y is in your conformal prediction set or interval is at least 1 minus alpha. And the nice thing is, the only assumption that you need for all this to work is the so-called exchangeability. So your training and test data needs to be exchangeable, which means that they are drawn from the same distribution and that their order does not matter. So it doesn't matter what is the first sample that you choose or the next and so on, which is a lower assumption or less of an assumption than the classical IID assumption that you have, which means that your data is independent and identically distributed. Okay, now we can look how that looks in practice. Here we have, on the left, we have the example for regression, where the non-conformity score could, for example, be the absolute residual. So your true value Y, which you get since you have this calibration set, minus the predicted value. So if we, for example, look at this example where we just have some kind of score and we want to predict our outcome, our prediction is the blue line here. We get a single observed outcome here out of our calibration set, and we see that this has a quite high non-conformity. So we can see that the prediction is quite far away from the true value. And now we basically just, we can do that for all of our calibration set. So all the dots that you can here see are points from our calibration set, and we just measure this non-conformity score for all the examples. So for example here, points that are very, very close to our prediction have very low non-conformity. They are very conform with our prediction. And we can then just calculate an interval. So we just take, for example, the 90% quantile here and say this is what we expect in future observations as well. We can also do the same for a classification case. So here the score could be 1 minus the probability that we predict, so 1 minus the predicted probability. And the set could then be all the classes below our quantile threshold. So for example here, if we have some fraud detection case and we have the different classes that we can predict, so basically the different actions that we can take would be approve, review, reject, sorry I'm moving, escalate or fraud, we can use our calibration data to figure out which threshold we need to choose. So for example, our non-conformity score would be very low for fraud, escalate or reject. But we don't know, basically those are the three options that we would keep in our prediction set. So those are the three plausible actions that we could take, and it shows you directly the use of this conformal predictions, because earlier maybe we would directly just get the prediction whatever, maybe something like that it is fraud, but the reality is that maybe it's actually not fraud, but we would just reject this case without escalating it any further. And this basically already gives you this idea that maybe like one single class to predict would not necessarily give you the full picture of how uncertain you are about the prediction, and conformal predictions give you a nice way to do that. Okay. So even though this is such a nice method, what are the caveats? We see that this coverage is usually marginal, which means that subgroups may be undercovered. So if we here look on this graphic, we can see that this overall coverage is at 90%, so our intended interval. However, we have maybe some subgroups which could be groups that you can build based on your variables, for example. We can have some examples where the coverage is much lower, for example, only 80%. And we wouldn't know which, or we would have to check which groups are undercovered or overcovered, because what we get out of this conformal predictions is just this 90% marginal guarantee. So this is what marginal means here. Those guarantees rely only on comparable calibration and deployment data. So it's very important that we understand what this exchangeability assumption means. I mean, it's not too high of an assumption, but still, if you just take very different, like you apply your model in a very different setting and you don't have this exchangeability anymore, then obviously the method fails. Also, the intervals can be valid, but still too wide to support a decision. Imagine we're in the classification setting and you're always predicting all the sets. Then in the end, there is no information in this, because you cannot make a decision if it always predicts you everything at the same time, which is also problematic, because you need a certain level of precision to actually act on those decisions. Also, it quantifies the prediction uncertainty, not causal identification, which means that you don't get like some causal valid expressions that, for example, certain variables are causing something or what drives the uncertainty and so on. So it's really just a method for uncertainty quantification. We acknowledge our funding and the copyright. Thank you, everyone.